Hello everyone, let's look over chapter 24, carbohydrate. It may be necessary to review following topics to prepare for mature in these chapters. So you can check uh, chapter 4 and 5 and 19. Carbohydrates are polyhydroxyaldehyde or ketones. Carbo means carbon, hydrate means H2O. General formula of carbohydrate is CH2ON. Poly means many, hydroxyl group OH, aldehyde, functional group RCOH, or ketone RCO double bond and R. So naturally synthesized in nature from the carbon dioxide and water. The monosaccharides. Mono means one. Monosaccharides are the simple sugars. Monosaccharides contains multiple chiral centers. For example, in glucose, you can see multiple chiral centers. Fisher projections, you can see Fisher projection here, often used to represent the structure. This is Fisher projection for glucose, this one, fructose. Aldose contains an aldehyde group, prefix aldo. In this case, this one, aldose. Ketose contains a ketone group, prefix keto. In this case, ketose. The term di, 2, tri, 3, tetra, 4, pent, 5, hex, 6, hept, 7 indicates number of carbons. In this case, 1, 2, 3, 4, 5 carbons. So we can call aldo pentose. So in this molecule, 1, 2, 3, 4, 5, 6 carbon. So ketohexoses. Classification of monosaccharide TNL. Glyceraldehyde. Glyceraldehyde is simplest aldose. Simplest aldose contains one chiral center. Here, one chiral center. So these sugars have OH group at chiral center first from carbonate. So in this case, you can see OH group at chiral center first from carbonate. On the right hand side, in the Fisher projection, we can call the sugar. In this case, the reverse. So on this OH group, so we can call the glucose, the fructose. There are four possible aldoheteros. So aldosis, then two chiral center. Two chiral center. Two are D sugar, and other two are enantiomer L sugars. So when you draw the L sugar, that's CO, OH, H, and HOH. Here, OH on the left side, CH2OH. That's L erythros. Now, when you draw L tereos, you can draw structures OH, H, OH, A, CH2OH. So there are four possible aldotetrosis. Tetro means four carbons. One, two, three, four carbons. Aldopentoses have a three chiral center. One, two, three, one, two, three, three chiral centers. The number of isomers will be 2 and exponent 3 equal 8 possible stereoisomers. For example, D-reverse, D-arabinosis, D-xylosis, D-lysosis. And then four more, L, 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 L. Total 8 possible stereoisomers in aldopentoses. These sugars are naturally occurring. And you see aldohexoses, 6 carbon, have 4 chiral centers. Possible 16 possible stereoisomers. The 8 naturally occurring D sugars and then 8 L sugars also. Total 16 possible stereoisomers. So when you see this one or D sugars. So let's check the configuration of aldose overview. This one, D glyceraldehydes, 1 chiral center, 2 chiral center, 3 chiral center, 4 chiral centers. So ketosis. Now can you see carbonyl group next alkyl groups? Then 1 chiral center, 2 chiral center, 3 chiral center. You can see examples of monosaccharide. Let's look over cyclic structure of monosaccharide. So aldehyde can react with alcohol to produce hemiacetal. So hemiacetal, on same carbon, you can see one OH, one OI group. That's hemiacetal. Hemiacetal formation is favored for 5 and 6 membered ring. In this case, you can see 1, 2, 3, 4, 5, 6 membered ring. So we can call this a cyclic hemiacetal. On same carbon, you can see one OH, one OI group. This is cyclic hemiacetal. So monosaccharide undergo ring closing hemiacetal formation. So this is a ring closing hemiacetal formation. On same carbon, you can see one OH and one OR. So cyclic hemiacetal. So equilibrium greatly favor the cyclic form. So when you see equilibrium, you can you see longer arrows? So equilibrium greatly favor cyclic form. This is the open form, cyclic form, closed form. 6-membered hemiacetal ring of a saccharide is called Pyranose ring. So memorize the Pyranose ring. Pyranose ring is 6-membered hemiacetal ring. Pyranose ring. Stereoisomers formed you often cyclization called anomers. So you can see alpha anomer. This is an alpha anomer. The anomeric OH groups. anomeric OH groups trans to CH2OH group. Now can CH2OH is the trans, opposite directions. So beta anomer is anomeric OH is cis to the CH2OH group. The same side. You can see OH and CH2OH. So we can call this carbon anomeric carbon. Anomeric carbon. So mutarotation, interconversion of alpha and beta anomers. This is the alpha and beta anomers. You can see equilibrium. Dynamic equilibrium between alpha and beta anomers is called mutarotation. Mutarotation is accelerated with acid or base catalysis. With some sugars, the alpha forms dominates, but beta anomers dominates for others. So pyranose ring is either drawing Howard's projection or Chap projection. The glucose is only sugars where all groups are equatorial. This is the glucose. You can see all groups are equatorial. So pyranose ring is 5-membered ring hemiacetal of the sugar. For example, 1, 2, 3, 4, 5-membered ring. On C2, can you see one OH when one OR? That's hemiacetal of sugar. So this is pyranose ring. 6-membered ring, hemiacetal of sugar. That's pyranose ring. That's different. 5-membered ring, 6-membered ring, 5-membered ring, pyranose, 6-membered ring, pyranose. So fructose, this is fructose, equilibrate among pyranose and pyranose. To generate pyranose ring, OH group SC5 attack to carbon. And OH group SC6 attack to carbon to generate pyranose ring. So pyranose ring forms the fructose. Fructose takes part in most biochemical reactions. Okay, let's look over reactions of monosaccharide. For example, let's prepare for ester number 1. Let's make ester. So hydroxyl group of monosaccharide. Hydroxyl group monosaccharide can be converted to ester to improve their solubility in organic solvent. So you might use excess acetic anhydride. Acetic anhydride is this one. And with the base. The excess reagents allows for the reaction of free hydroxyl group. There are many free hydroxyl groups, right? Also, reaction number 2. Let's make ether. So hydroxyl group can be also converted to ether. ROR, ether. You can use excess metal iodide with the base. Silver oxide is used as the base. So this is William ether synthesis. We can generate ether, William ether synthesis. Okay, next, let's make glycoside. Glycoside. Cyclic hemiacetal. Cyclic hemiacetal of a sugar. The same carbon, you can see OH and OR groups. Cyclic hemiacetal of sugar can react with an alcohol under acid condition, in this case HCl, to form acetal. Acetal means on same carbon, you can see two OR groups. Same carbon, two OR groups. You can get mixture of glycoside. The mixture of alpha beta glucoside is obtained. So now can you see OCH3 to the bottom, you can call alpha. So OCH is to the top, this way, that's better. Okay, let's look over the mechanism. Mechanism of glucoside formation is analogous to formation of typical acetal. So proton transfer step, rearrangement, you can get resonance, stabilize carbocation. Carbocation, stabilize carbocation. Then we can generate formation of that one, beta, this one, alpha. Methanol attack to carbon, so carbon to generate the beta glucoside. And the other side attack, and then we can generate alpha glucoside. The reaction of the monosaccharide number 4, epimers, under strongly base condition. For example, when you use strong base, NaOH, aldose undergo epimerization as C2, C1, C2 here via endiol intermediate. So base deprotonate this proton and rearrangement, you can get N diol. And the base deprotonate and proton transport, you can generate the glucose and the mannose. So epimers are diastereomers, differ in configuration at only one chiral center. So only you can see one different chiral center. You can call this one epimers. Epimers. Reaction number 5, reduction of monosaccharide. Monosaccharide can be reduced to alditols with sodium borohydride. So aldehyde to primary alcohol by using reducing reagents. D-glucitose is used to a sugar substitute. And reaction number 6, oxidation. Aldehyde oxidation of aldose produces aldonic acid. This is aldonic acid. Variety of oxidants can be used. In this case, we can use bromine and water. So mild oxidizing reagent must be used to avoid oxidation of alcohol group. You can see alcohol group. We need to use mild oxidizing agent to generate carboxylic acid to avoid oxidation of the alcohol group. Okay, test number 7. Reaction of my monosaccharide number 7. So selective oxidation of aldose, not ketose, is used as chemical test to differentiate between aldose and ketose. Oxidation test performed to detect presence of reducing sugar. For example, pyranose form of sugar. You can use tolerance test, pairing test. Glucosides are not reducing sugars, are not oxidized. Okay, reaction number 8. Let's make aldehydic acid. Stronger oxidant like HNO3, nitric acid, will oxidize aldehyde and primary alcohol of aldose. This is aldose, aldehyde, and primary alcohol. And you can see also secondary alcohol here, secondary alcohol. But you can oxidize aldehyde primary alcohol to carboxylic acid. This is aldehydic acid, Mild oxidizing agent must be used to avoid oxidation of alcohol group. If you use stronger oxidant, you can convert aldehyde and primary alcohol to carboxylic acid. Reaction number 9. Let's make cyanohydrin. So recall cyanohydrin formation. Cyanohydrin formation, it works on aldehydes. For example, this one looks like aldehydes, right? When you add hydrogen cyanide, you can get cyanohydrin product. When you look at Piliani-Fischer synthesis, cyanohydrin is hydrolyzed to carboxylic acid and subsequently reduced to what? Aldehyde. That Piliani-Fischer synthesis, cyanide to aldehyde. So overall Piliani-Fischer synthesis lengthen carbon chains of sugar by one carbon. So now can you see on sugar through Piliani-Fischer synthesis, you can generate length one carbon. Synthesis length carbon chain of sugar by one carbon here. So cyano group can be converted to aldehyde in one step. Cyano group to aldehyde in one step. What do you need to use? Hydrogen, palladium, barium sulfate, and water. The one step. The cyanide group to aldehyde. In one step, you can use hydrogen, palladium, barium sulfate, and water. For example, D-arabinose, you can use two steps. Okay. Step 1, add hydrogen cyanide to generate and cyano formation OH, H, and CH2O. And also you can generate mixture HOH, OH, and C2OH. Step 1. Then when you add step 2, you can generate a product. So basically all the same, but you can insert one carbon chain here. So reaction number 10, Hoyle reaction. Hoyle degradation achieved opposite of Galliani-Fischer synthesis. It shortened the carbon chains by one carbon. So you can use hydroxylamine. So D-glucose react with hydroxylamine to generate oxime. Oxime. And then as an anhydride, you can generate cyanohydrin. Then proton transfer step, you can get arabinose, the product. So basically, aldehyde, the same. This part all the same. You can remove this one. To shorten the carbon chain by one carbon. Okay, next, we need to look over disaccharide, glycosidic linkage. Di mean two. Can you see? One and two. Two saccharides. Disaccharide consists of two sugars connected through glucosidic linkage. We can call this one glucosidic linkage. Glucosidic oxygen connect C1 to C4. C1 to C4. So this is 1, 4 disaccharide. Mildose is reducing sugar because when you look at this carbon, you can see one OR group, one OH group. This is 6 membered ring hemiacetal of sugar. That's why this is reducing sugar. Let's check stereochemistry. So cellulose and maltose only differ by the stereochemistry at the anomeric carbon. When you see anomeric carbon, this one C1, you can see alpha glucoside. To the bottom, C1, you can see beta glucoside. This is alpha pyranose. This one is beta pyranose. So in disaccharide, you can see lactose. So lactose disaccharide. This is lactose. So now can you see C2, the beta, the 1,4-glucoside. That's lactose. The second example, sucrose. Sucrose is a disaccharide. 1 and 2 disaccharide. Sucrose is not reducing sugar. On same carbon, you can see one OR. And then this is not OH. So not reducing sugar. Okay, next, let's look over polysaccharide. For example, cellulose. This is cellulose. Cellulose is a polysaccharide containing 7,000 to 12,000 glucose unit. This is glucose connected through beta glucosidic bond. Now, can you see beta glucosidic bond, beta glucosidic bond? Cellulose strands strongly hydrogen bond with another, giving wood and plant mature their rigid structures. Second example, starch. Starch is also compromised of glucose unit connected by glucosidic linkage. There are two components, amylose 20%, 80%, aminopectin. So when you look at amylose, you can see 1,4. C1, C4. So alpha, alpha glucopyranoside polymer. That's amylose. And then when you look at aminopectin, has glossy branches of C6. At C6, you can see 1,6 branch. That's aminopectin. Okay, next, amino sugars. Amino sugars, you can see amine group and sugar. Amino sugar like glucosamine are important biomolecules. Acetylate, acetylate glucosamine. Acetylate, what does it mean? CH3CO. That's acetyl group. And glucosamine forms important polysaccharide called chitin. Chitin, this is chitin. And acetyl groups allows for even stronger hydrogen bonding between neighboring chain than cellulose. Next, let's remove N-glucoside. N-glucoside. N-glucoside are formed by reaction with amine under acid condition. So nitrous base pair in DNA are connected to the deoxyriboose unit via N-glyceric linkage forming nucleoside. So ribose form ribose nucleoside in RNA. Deoxyribose form deoxyribonucleoside in DNA. So now SC2, you can see OH group. SC2, there's no OH group. This is ribo nucleoside. Deoxy, there's no OH group. So deoxyriboside. There are 4 different heterocyclic amine attached to deoxyribose. Deoxyribose. You can see 4 different heterocyclic amine. So this is cytosine, this one thymine, adenine, guanine. In DNA nucleoside, you can see cytosine, thymine, adenine, guanine. In DNA, nucleosides are attached to phosphate group. This is phosphate group, forming nucleotide. This is nucleotide. Phosphate group of nucleotide are connected to make a DNA strand. The polynucleotide. So phosphate group, phosphate groups of nucleotide are connected to make DNA strand. You see the base chain, thymine, cytosine, adenine, guanine. Nucleotides in DNA can attract another through the hydrogen bond of DNA base pair. So DNA base pair, for example, cytosine, guanine. Can you see red dot line? That's hydrogen bonding. And DNA base pair, adenine, thymine. You can see also hydrogen bonding. The RNA is structurally different from the DNA. The sugar in RNA is reverse. You can see C2 hydroxyl group. RNA contains uracil instead of thymine. Uracil, this is uracil. RNA translates information stored in DNA into working molecules. Here is RNA strands. Thank you for watching video.